Alright, hello, my name is Matthew Frost. I'm going to be doing a presentation for you on stellar evolution, which is essentially how stars are born and their lifespan. It's very, very simple. I'm going to walk you right through it. We'll have no problems. I'd like to, first off, apologize for the terrible mic quality. I know my laptop's getting a little bit old. There's literally chunks falling out of it. So, mic might not be necessarily the best thing you've ever heard, but we'll make do. Alright, let's dive right in. So we're going to be starting with the Hertzsprung-Russell diagram. It's fundamental to what we're going to be doing, and it kind of gives you, a basis, kind of it puts us all in a level playing field when I start this presentation. So what does the Hertzsprung-Russell diagram do? It shows where other stars are plotted against each other by the temperature and brightness, and it also helps us to find out how far away these stars are, how old they are, and what type of star they are. Alright, so just by looking at this diagram, you can determine the life of the star. It's very useful. So, this is the diagram itself. I'm going to be using the sun for an example. Alright, so don't worry about spectral class, don't worry about that. Let's say we know that the luminosity of the sun is 1. Yep, very simple. We also know that its class is G, so the sun is a G class. It's actually a G2V class, but don't worry about that. So we know that, and from there we can plot the point, and from there we can find out absolute magnitude, which is its natural brightness, I suppose, and we can also find out temperature, and we can do it vice versa. There's so much we can do with this for tons and tons of stars, right? You can see there's a bunch of different groups. We have the main sequence, which is about 90% of all the stars on this diagram. Then we also have supergiants, which are very luminous, although fairly cold. Giants, which are not quite as bright, not quite as luminous, but still fairly cold. And then we have things like the white dwarfs, which are incredibly, incredibly hot, but they're very small, right? So they're not very luminous. And this kind of, this whole chart kind of ties into what we're going to be doing today. So let's start with the actual basic part of the presentation, star birth. Alright, so star birth is how a star is born. It speaks for itself, you know. So, it starts off, the star is born in a big cloud of gas called a nebula. Alright, so this is a picture of one right here. You know, it looks just like this. There's lots of gas and particles floating around. They've all come together because of gravity. Right, and gravity plays a big role in this because gravity, because of gravity, the gases and the particles will start to move toward each other. I beg your pardon. And because of this, as they start to move toward each other, they begin to rotate. You can kind of see it starting to happen here. And they start to clump together in little tiny balls. All right, and as they rotate, they get closer and closer and hotter and denser. Right. I like to think of this as a snowball. Right. You have a big open area of snow, and when you make your snowball, you have to bring all that snow in. Right. So you're taking a bunch of snow, and you're in a wide space, and you're putting it into a small space, like a snowball. And you're squishing it all together, you're making it really, really close, right? You can all relate to that. It's very simple. So it's the exact same thing. Okay? Eventually, after this happens, the stars will reach a temperature of about 10 million degrees Celsius, and fusion, which is taking hydrogen and turning it into helium, will happen, and this creates a lot of energy. It makes the sun and stars very, very hot. Right. So at this point, the star's life will have begun. Before now, it's been known as a protostar. Right. So there are two main groups of stars. There are average mass stars, and then there are massive stars. And we're going to be talking about massive stars just a little bit later. So average mass stars are less than 5 times the size of our sun, and they have a very, very long lifespan of about 10 billion years. And our sun is about not quite halfway through its lifespan yet, which is good news for us. Hopefully the human race can survive long enough to see it end. I highly doubt that, but you can hope. So after the star's been born, these are the main phases that the star will go through if it's an average mass star. Okay? So red giant, planetary nebula, white dwarf. red giant, planetary nebula, white dwarf. There we go. So this is the sun today. It's still fairly new, so it's very, very small. It's still just been born, kind of, you know. But when it turns into a red giant, which will be in about 5 million years, it'll become very, very bright and about 100 times larger. You can see that right there. From then, it becomes a planetary nebula, and from then, it becomes a small, small white dwarf. This is definitely not to scale. The sun will never be this close, well, hopefully, to the Earth. And then, that's it. That will probably be where it ends until it cools off into nothingness. So, let's recap this. Average mass stars, they make energy from converting helium to hydrogen, known as fusion. Alright, and this energy tries to push against the gravity of the star. So what I like to think about this is that it's kind of a complex idea, but I like to think of a balloon. Alright, so the balloon is the sun. We'll use this circle here. The balloon is the sun. Okay? And the sun has energy pushing out against the gravity that's holding it in. And just like the balloon has air pushing out against the plastic outline of the actual balloon itself, right? And the balloon itself, the plastic, is kind of like the gravity of the sun or the star, right? It's the exact same thing. So it's kind of a balance that's going on. They're finding an equilibrium, and that's how big the star is determined. Alright, so that would be average mass stars. Now we're going to go into a little bit more detail about red giants, planetary nebulas, and white dwarfs. So red giants, eventually, the star won't be able to change any more of their hydrogen into helium. There'll be a little left, granted, a little bit left, but it's going to be mostly converting helium into carbon. But yeah, so the outer layers of the red giant, or of the normal star, will cool and expand, which will create the red giant. And this will happen in about 5 billion years, and the red giant phase will last for about 100 million years, which is very fast in the history of the universe. This is a little diagram of what it's going to be like, right? So the sun is, this is definitely not to scale, but the sun is pretty small here, and then when it becomes a red giant, it's going to be huge, right? So, as you can tell, this will definitely not be good for life on Earth. It's going to be very, very hot for us. The sun will be closer to us than it is close to Mercury right now, and Mercury is a very, very, very hot planet. So, after the red giant phase, will become, or the star will become a planetary nebula. So once the red giant phase ends, the star expands really fast, losing all of its smaller, lighter outer layers. Right, and then there's going to be a small core of carbon and heavier elements that will remain on the inside of this cloud. So you can kind of see it right where my mouse is right now. This is the same as a white dwarf. Right, so the core from the planetary nebula cools, and all of the gases and stuff kind of drift away off into space. So this leaves a white dwarf, which is a very little star with tiny amounts of energy coming from it, and it's cool and very, very small. So if this is the sun now, right here, this would be the sun as a white dwarf, which would be in about 6 billion years. So now that that is out of the way, we're going to be talking about massive stars, which is the other group I talked about before. Right, so massive stars and then average mass stars. So massive stars are at least 5 times the size of the sun, so at least 5 times bigger. They're very, very short lifespans, which are less than 10 million years, which is very short in the whole timeline of the galaxy. And the way I like to picture massive stars versus average mass stars is by fires, right? So let's say you have a normal fire in your fireplace. Okay, it's just normal, you haven't done anything to it, you just leave it, and it's going to burn fairly slowly. It'll take maybe an hour or two to completely burn out. And that would be average mass stars. Now massive stars, I like to think of, you take a bonfire outside and you pour like 10 gallons of gasoline on it, okay? And obviously that's going to make it explode, and it's going to burn really, really fast, and it's going to be super, super hot, and it's going to be out in under 30 minutes. It's the same thing with massive stars. They burn so hot and so fast that they use up all of their energy, So the first stage after it's been born, and this takes many years to get to this stage, mind you, would be the red giant. So these are made up of many different types of elements, just like all stars. And these stars have lighter elements on the outside of them, excuse me, but heavier elements on the inside, and it has a core of iron. So this is a little example. I believe this is Betelgeuse, one of the closer red giants to Earth. And so this is the size of the star. This is to give you a little idea about how big it is. And this is Earth's orbit around the sun right now. Right? So obviously, if the Earth were to orbit around this star, it would be basically on the inside. It would be burned up. Right? And this is the size of Jupiter's orbit. So try and picture in your mind the vast, vast size of the universe. It's just humongous. It's bigger than you can even imagine. Alright, I'm sorry I made you try, because it's really, really hard. The universe is huge, huge. So this is kind of just a little depiction on how big it actually is. And so after the red supergiant phase, there will be a supernova, which is a really awesome explosion. Okay, eventually, there's no more pressure coming out from the core of the red giant, or red supergiant. Alright, so what happens then? The star collapses incredibly fast, and then it reaches kind of a tipping point and it explodes. Alright, so this is a picture of one here. I'm going to give you a little zoom up or soon. So it blows away all the lighter outer layers of the star. So this right here would probably be oxygen, a little bit of helium, really light elements like that, right? So it's a picture for you. Okay, so that's the inside. That's where the explosions happened. Ooh, sorry. So after this phase, depending on the size of the star, there are two distinct possibilities. And the first one is neutron stars. So this will happen, a neutron star will happen if the massive star is less than 15 times bigger than our sun. So does that make sense? So it's less than 15 times bigger than our sun. It is very, very dense, but it's a small star. And again, I'm going to use a snowball analogy, right? You take a large area of snow, light, fluffy snow, and you pack it all together really, really tight, and you've used up a large, large area, and you've put it into a really, really small space. So it's the same thing with a neutron star, except on a much, much bigger scale. This star is 20 kilometers across. Okay, our sun is huge. It's much, much bigger than that. But this star, it's 1.5 times the mass of our sun. So it's small, but it's really, really, really heavy, right? Think about, you go to pick up a pebble, alright? But this pebble weighs like 4,000 pounds, okay? You'd probably break your fingers trying to pick it up. It just wouldn't end happy for anybody. Okay? It's kind of like that. It's super small, but it's really, really heavy. Okay, it also has huge electromagnetic fields and the other stuff like that. Right? It also has massive electrical charges. So the other possibility would be for this star to become a black hole. And this happens if it's bigger than 50 times the size of our sun. So if it's already a very big star, then this is probably what's going to happen to it. So black holes have huge gravitational forces, and it kind of sucks everything into it. Right? And this would be basically the end of the life of the star. Okay? So, that is that. Thank you for listening to me. I know I've probably rambled on a bit. I hope you enjoy this. I hope you've learned something. And this was Matthew Frost on Stellar Evolution. Thank you very much.